seminar stuff or
Hello, everyone. This is Paapa Kwesí from Electrical 3. And sorry for the too many delays in the microprocessors. We found conflicting ideas here at the studio, so wanted to clear them up before we began the live stream. And also, we had some complaints that there are a lot of questions, so we wanted to distill it as much as possible to the ones which we really believed will come. You understand? That was the reason why we kept so long. So we're now here. So we thank you so much for being with us. So we'll begin. We'll begin very very soon. We'll begin very very soon. And so before we begin, I wanted to do this some time ago, but I didn't get the chance to. We want to thank every single person. It's been a long journey. It's really been a long journey. 5 months ago, I think, yeah, tomorrow will be our 5 months anniversary, 3rd February. Right. So we want to thank you for almost beyond 550 subscribers, over 15,000 views, 750 subscribers, over 15,000 views, beyond 3,000 watch hours. We'd like to thank you so much, and thank you for all those who are sending in their support in cash and kind. We've gotten so much sponsorships left and right. We're getting sponsorships left and right. So we want to thank you for being part of the Elisa journey. And this, if you're unable to finish tonight, or we see the need tomorrow morning, we would have another stream. But if not, tonight will be our last stream for the semester. Tonight will be our last stream. So let's go and clock the micro P. Okay, so as usual, check the description boxes, contact your friends, text in the chat. This is very, very important. This is very, very important, Charlie. If we're going to the class the entire semester, please focus with this one so that at least you'll be able to get 40 over 40 and then be proud of your mark. You understand? You know what you went to do in the project. You understand? You know what you went to go and do. So please be on point. So as usual, check the description. When you check the description, you see two different links. We're going to start with the one on the top. Laura Kote, hello. Paul says hello from this side too. So yes. Yes. So please check the description. The first one will be the link for the one that we'll be using. Right. Yes, that's the 2020 2021 questions. We'll skip the first question because it's an address decoding question. He told us it won't come, so not to waste anybody's time, we'll not do it. But
all this security happens.
Okay, so please let's go. No, cloud high. It's not only you. I went off for a moment to check up with something else. Okay, so please let's move. Okay, so yeah. Hey, please let me know.
And you can also see all other videos, all the other story.
Okay, so yes, we are here. So I was just getting the question ready. So yes, please, here's the question. And as I said, question one is not, we won't talk about it because it's an address decoding question. And we expect no address decoding questions to come by courtesy of Dr. Yankee. But if it comes, I hope it won't come. Question two. So this is where we want to start from tonight, right? This is the question. So let's go. So I really believe that this question is coming. So let me talk about what I think the questions, how most questions will be. I think question two, this particular question will come. And so don't hold me at my word. This is just what I think. Yeah, this is just speculation, right? If anything changes in the speculation, as I said, we'll have a stream tomorrow and then we'll rectify that. But basically, question two would come. Question three. Right, question three will be explain. So they'll give a couple of statements. So we'll look to the types of statements that they can bring from other past questions. But basically, there will be an explain question. That'll be where you'll be asked to explain some concepts. Right, and then question four, we hope that it will be assembly language. And question one will be the interrupt and then the polling. Right, so that's what I think would be tomorrow's question. So please let's go ahead and then let's solve the ISA question. The following text describes an ISA referred to as the YKS architecture. Note, this is a contrived example. All instructions in the YKS ISA are 2 bytes. The first, so let's take note of this, right? All the instructions are 2 bytes. The first 3 bits represent the addressing mode. So first 3 bits. So this is how I want you to think about it, right? I want to think about this. So this is how an instruction is. This is how an instruction is, right? And you see, we are reserving the first 3 bits for operating mode. So this is op mode.
Addressing mode.
Oh yes, sorry, addressing mode. I'm reserving it for addressing mode. They're reserving the first 3 for addressing mode. So this for addressing mode. And because let's look at how many words they said it is, right? They all instructions in the YKS ISA are 2 bytes. So we expect this to be 2 bytes. 2 bytes meaning 16 bits. So there'll be 16 individual lines here and 3 is gone. So these are 13 left. 13 left in our address. Beautiful. Okay. So all supporting addressing modes are given in table 1, right? So table 1 is here. This is table 1. So these are all the addressing modes available in the YKS architecture. I hope you understand. And so these are decimal numbers. So it is from 000 to 001 to 010 to 011 to 100 to 101. Yes. So these are the 5 different modes that we have in our instruction. So everything else I don't care. So if you have an instruction that starts with 111, you know that it's an invalid instruction from the beginning. No, you know that because we don't have any addressing mode that corresponds to 111. Okay, let's move. So for 0, we have intermediate to register instruction addressing mode. Sorry, we have register to register, register to memory, register to memory. So you will get to this one, register to memory to register, and then intermediate to memory. Excellent. The next 5 bits represent the opcode. So one, two, three, four, five. They represent the opcode. So the next 5 represent the opcode. So 5 minus 13 minus 5. So 8 remaining in the system. 8 bits that we don't know what they are for in the system. So please, hello. Sorry for the another interruption here. I'll be back very, very soon. In the next 2 minutes, we want to check something with the links. Someone said something.
Okay, so Papa will be back soon, but then I'll take over for a little while. So then in the in the question, we already spoke about the addressing modes. So then we have 3 bits. The first 3 bits representing the address modes, and we spoke about the address modes. 0 representing immediate to register, 1 for register to register, 2 for register to memory. Let me see. 2 for register to memory, 3 for register to memory 2. But then for 2, okay, so this one Papa said we'll come back to it, but let's just describe it now. So for the 2, the memory location is specified by another register, which means that in this kind of addressing mode, we'll specify a memory location, but then we'll indirectly we'll specify a register before. So we specify a register which will point to a memory location. So then we specify a register, and then behind the scenes, the microprocessor will go into that register to fetch a memory location for us to go to. But then in the number three, that's also registered to memory. But in that case, the memory location is specified by an immediate value, and an immediate value is basically just a constant. So then in that case, the immediate value specifies the actual address of the memory location that we want to go to. So I hope you are clear on that one. For the second one, which is registered to memory, where memory location is specified by another register, we specify a register and then another register, and in the second register, that's where we get our memory location from. Then for register to memory, the second one, the memory location, so we specify one register and then we specify an immediate, which is a constant, which itself is our memory location. The fourth one is memory to register, and the fifth one is immediate to memory. Okay, and then the second table. Okay, so before we move to the second table, the preamble says direct memory to memory operations are not supported. So we can have an addressing mode which is memory to memory. However, they may still be implemented in the higher level assembly language. In this case, the assembler will simply convert the instruction to two separate instructions and use any available register as an intermediary storage. So then for this one, we can't directly specify a memory location and another memory location. But then what they are trying to say is that there can be assemblers that will implement memory to memory operations, where those memory to memory operations will be translated to two memory to register, as in one from maybe register to memory and the other from the memory to register, so that it look like it's from memory to memory. I hope that was clear. I don't even think we need that one as we are moving on. Then the next 5 bits, as you said, is for the opcode. So then the opcodes, they are like all possible opcodes are supported. Yeah. So every possible opcode is supported. And then there are some supported opcodes shown in the table too. So then the first opcode that is supported, the first opcode that is supported, that is shown in the table is 00000. 00000, yeah. Okay, sure. So then for that one, is it has the mnemonic of load, which means load data from source to destination. For 00001 is the same as 00000, and the mnemonic is move it. Okay, I'm not clear on this one, but I think it will be clear as we move on. Then 00010 just says we should add two operands, and the mnemonic is plus. Then 00011 says we should subtract two operands, a source from destination, and the mnemonic is minus. So mnemonic is basically what we use in the assembly language, right? Okay, so let's move on. And then the next 4 bits, represent the first operand, and it's always the destination, which means it's similar to the x86 instruction set, where, let me see, I'm coming, 1 minute. Yeah. Thanks. Okay, so you're back. The next, so we said the first 3 bits addressing mode, next 5 bits opcode, and then the next 5 bits is, let's see, sorry, is it next 4 bits? Next 4 bits is, let's see, where is it? Okay, which side? Okay, next 4 bits represents the first operand, and it's always the destination. Okay, so it's like, okay, so next 4 bits, the forgive my writing. Let me see. Let me just use a different. So let me just write it like this. Okay. Okay. So next 4 bits represents the operand, the first operand, and it's always the destination. So if you're writing it in assembly language, it looks something like maybe if you have if you are performing an addition, it look like plus, then the next 4 bits will represent the operand. So maybe the operand is a register location, so something like AX, right? And then BX, where AX is the first source operand and it's also the destination. So if you are this instruction is trying to tell us to add what is in AX to what is in BX and then store the result in AX, right? Okay, so that's basically what it means there. And then the last 4 bits represent the second operand and is always the source. Okay, sure. So then there are 16 available registers, AX to PX, and register A is addressed with the value 0, B with 1, C with 2, D with 3, and so on. This continues to the last register P, which has the address 15. Okay, so AX has 1, BX has 2, up to 15. So it's EX, FX, GX, HX, like so. So GX would be 8, and then yeah, we move. Based on the YKS architecture, answer the following instructions. So they're like, how many different unique 4 instructions can be accommodated in this ISA? So remember to take out the unsupported instructions. So I'm coming. When they say unique, okay, so unique instructions means basically every sequence of bits is unique. So it's not just that the add instruction is unique from the subtract instruction or the plus instruction is unique from the minus instruction. We are considering every unique sequence of bits. So we are considering every possible sequence of bits that we can get, but we're supposed to remove the unsupported instructions. So we refer to our annotations. So first 3 is address mode, second 3 is opcode, third 3 is destination, and then third 4 is source, destination, and then last 4 is source, right? Okay, so we have 3, we have 5, we have 4, and then we have 4. So then how many possible, so the only supported addressing modes are from 0 to 5, right? So we have only 5 addressing modes. Sorry, 6 from 0 to 5. So we have 6 here. So we use something in the order of permutation, like we are permuting the number of possible unique instructions that we can get. So for the 3, right, for the 3 bits, so it's like, okay, I don't want to draw it again, but you see here, forgive the writing again. So for the address mode is 3 bits, right? But then of the 3 bits, only 6, we can only input 6 unique 6 values here, right? That will be supported. So that's 000 00 1 010 00, sorry, 011 and 100. So that's 5 of them, right? Okay, sorry, 6 of them. So yeah, plus, okay, so 111 is also supposed to be, but 101, okay, 101. So that's, yeah, 111 is not part. So let me take 111 out. So 111 is not part. Yeah, let me make sure that's the way it says in the question. So yeah, so there are 6 of them. All right. So we put 5 here. So 5. Sorry, I think I prepared that one. Okay. So 5 here. Let me erase the rest of the things from here. So we put 5 here because you can only have 5 possible permutations in the first spot. Then for each of the 5 possible permutations, all the opcodes are supported. So then, because it's 5 bits, we have 2 to the 5, right? And 2 to the 5th is 32 possible permutations. So we can permute the 5 bits 32 times to get 32 unique 6. Okay, so this one is 6, sorry. Here's 6, I made a mistake, sorry. Let me just erase it and then put 6 there. Okay, and then the next one is 2 to the 5, which is 32. So we put 32 there. And then next one is 4 bits, which is used to supply either, so it's used to supply a destination, and then the next 4 bits used to supply a source. And for our source and our destination, let's look back to the question. See if our source and destination are actual numbers or just registers. So let's see. The last 4 bits represents the next 4 bits represents the first operand, and it's always the destination. And the last 4 bits represents the second operand, and it's always the source. And they can be immediate, right? They can both be immediate, which means they can both be normal constants. So if you are considering normal constants, then it means ideally our constants should be able to span all the 4 bits. So from the number 0 to the number 16, sorry, 15, which is 16 possible numbers. So 2 to the 4 is 16. So that means from 0 to 2 to the 4 minus 1. You understand? So there's 16 here, and then there's 16 here. Aside from that, they say there are 16 possible registers that we can use. So we can also use that one. But I used immediate because even if we had like 8 possible registers, our immediates could possibly still span the whole instruction size, right? So then 16 and 16. So then the number of unique instructions that we can have is 6 times 32 times 16 times 16. Okay, so we can compute that. The result. Okay. 3 by, okay. So we have, sorry, 3 by 2 to the 5 plus 4 plus 4, and that's 14. 14 or 13. Okay, okay, sure. So so 3 times 2 to the 14. So I'm sure you can evaluate this, and then that will be the number of unique instructions that we can have. Um, sorry for the jitters. I'm not used to the pen. But then yeah, that's it for A, right? So we can have 3 times 2 to the power 14 unique instructions, right? That's when we take out the unsupported instructions. The next question is, how many different unique opcodes can be accommodated? For the different unique opcodes, I think we already went through that. So all the 5 bits, we use 5 bits for the opcode, and in the question they specify that all possible opcodes are supported. Every possible opcode is supported, which means that every combination or every permutation of the 5 bits, every permutation of the 5 bits that we use for opcodes is supported. And when we permute 5 bits, we get 32, because permuting 5 bits gives us 2 to the 5, which is 32, as we stated here. So then for the second question, um well, it's not that difficult, so it's just 1 mark. So we can have 32 possible unique opcodes. Then what is the largest value of an operand? So the largest value of an operand, we have also done that one here. So the largest value of an operand is so you see our 2 operands, our first and second operands both take 4 bits, right? And when we permute 4 bits, we get up to 16 values, right? So we can have 16 possible permutations of 4 bits, but they are not asking for the number of possible permutations. If they ask for the number of possible permutations for the operands, then it will be 16, but they're asking for the largest possible value, and the values are 16, but they are from 0 to 2 to the power 4 minus 1, right? So 0 to 2 to the, sorry, let me use the pen. 0 to 2 to the 4 minus 1, right? Imagine 2 to the power 4 minus 1 in brackets, and that's from 0 to 15, because 2 to the 4 minus 1 is 15. So the answer to the next question is 15. So the largest value of an operand is 15, right? What is most likely the size of register dx? Okay, let me see. The size of register dx, what do they mean by this? Okay, as in, okay, I think for here they mean, let me consult Papa. um Okay. They are like, what's the most likely size of register DX? And the size of the register, or the size of a component, if the component is a register, then it most probably means the amount of data that it can store. And DX is possibly going to be like any other register here. So then it is going to store the same amount of bits as any other register here. Um, just that the question was being very specific with DX. Now, for the immediate, yeah, for the immediate, which one? Okay, given that instruction. Okay, let me see. Please 1 second. Okay, let's finish this one first. Let me see. Okay, I was initially thinking something different, but it looks like let's see. Where's the question? Okay, yeah. So so I was initially thinking something different, but it looks like for the register. So ideally, for a lot of architectures, when the CPU is executing instructions, the instruction is usually put into a register, like before the instruction is executed, as in the case of registers like program counters, right? So then, since the instruction goes into a register before it is executed, then the register should be able to store the same number of bytes as the number of bytes of the largest instruction. Now here they are like all instructions in the YKS ISA are 2 bytes, right? So then, since all instructions are 2 bytes, then each register should be able to store a minimum of 2 bytes. So the most likely size of register DX would be 2 bytes. Yeah, at least based on that analysis. Maybe we'll come back to this side because I'm not entirely sure of that analysis, but from a different source, that is the answer that they give. Okay. Then the next one is convert the following high-level assembly language programs to machine code. As is common in assembly language, memory references are made using a register in square brackets. Okay, sure. So then they are like load JX 10H. Sure. So then we have to translate load JX 10H to machine code. Sure. So then we need to consider a few things when you are translating from machine code to when you are translating from assembly language to machine code. Sorry if the live stream is going a bit slow. I'll try to speed up. Okay. So then converting the first instruction. Let's see. Load JX 10H. So it's a load instruction. Let's move to the table. Load has its opcode to be 00000, right? Okay. So first of all, we specify the addressing mode, but we already have the opcode, so let's write that. So let me see the addressing mode. You don't know that yet, so I'll leave a blank space here. But then the opcode is, sorry, um 00000. So 5 bits, right? And then the addressing mode. Now GX is a register, right? And then 10H is a memory location. Is it? Yeah, it's a memory location. So then we are using an immediate to represent a memory location, right? So then let's see. The addressing mode is immediate to register. So that's the first one, because immediate to register means that the register is the destination and then the immediate is the source. So then how do I say it? So it is 000000. Sorry, just 3 zeros. So 000. That's the addressing mode. I'll go over one more time. So it is loading from memory location 10H into GX. So the addressing mode is immediate to register, right? Because there's an immediate here specifying a memory location. So we are loading from a memory location into a register. So load data from source to destination, right? Okay. And immediate to register is represented by 0. That's the machine instruction in decimal, as stated here. So when you translate it to binary, and it has to be 3 bits, we get 000, right? So you have the first part, or the first few parts of our machine code. I hope everything is clear up to this point. Let me see. Then the next few bits is used to represent our destination operand. Sorry, so they are like here. The next 4 bits represent the first operand, and it's always the destination, right? So since the next 4 bits represent the first operand and it's always the destination, then GX is our destination. So then we look here, and then well, we can see from the table that GX is around 10 because A is 1, B is 0, wait, is J 10. So E will be 4, F will be 5, E, F, G will be 6, H will be 7, H, I, G, right? So H will be 7, I will be 8, and then J will be 9. Okay, so J will be 10. So J is 9 rather. So since J is 9, that means GX will be the binary digits for 9, which is 1001. So that's 1001. 1001. Like so. Then the next one is 10H, which is in hexadecimal, right? So in hexadecimal we just, let me see. Okay, so it's 10H. Let me see. 10 in hexadecimal as well. How do I see it? Okay, it's basically the same thing. But in binary it is 1010, right? So 1010. So I hope that was clear. Yeah, so the H just means it is in hexadecimal. So we have 10 in hexadecimal, which is the same as 10 in decimal. And 10 in binary is 1010. So we've translated the first instruction to machine code. The beginning part is our addressing mode, the first 3 bits. Then the next 3 bits, sorry, the next 5 bits are our opcode. Then the next 5 bits was our source, sorry, our destination. The next 4 bits rather was our destination, and then the next 4 after that was our source. Okay. So that's for load GX10. Then you have load BX GX. For load BX GX, it's almost the same thing. Okay. maybe it's not almost the same thing, but then our output is the same. So the output is 0 0 0 0 0 because the output for load is 0 0 0 0 0. Then we come to the addressing mode. The addressing mode is from memory to register, right? This one is from memory to register. One would think is register to register because GX is a register, but then GX is in square braces or square brackets, which means that this is an indirect reference to memory, which means that we first go into the register location specified inside the braces, and then we go and find a memory location there, and then we take whatever is in the memory location and put it in register BX. You understand? So this just means that load go to register location GX, you find a memory location there, and then whatever is in that memory location, load it into register location BX. So this is also a memory to register addressing mode. So it's a that's also we haven't had any yet. Yeah, it's memory to register. It's just that the memory location is specified by another register. You understand? So the memory location is specified by GX because GX is in square braces. We know that it's a register location by specifying the memory location, and then the second one is our destination is a register location. So then the addressing mode is here. So that's this one, number 4, and number 4 is 0100. Okay, so that's 100 when we chop off the first bit. So 100, that's for our addressing mode. Then our first operand. So our first source operand is BX, right? And that's the destination. And BX is just the second register in our table. So BX is 0001, right? Okay. So 0001 because 2 in binary, sorry, 1 in binary is 0001, and then we add extra zeros in front of it because it's supposed to occupy 4 bits. Then the next operand is our source. Now the source here is a register location which will specify a memory location we should go to. So the register location is given by GX, and GX we said was 9, the number 9 here. So then okay, there are questions in the okay, sure. Okay, okay, there are questions in the chat. Okay, can you write the answers to the by okay, sorry, okay, I'll write the answers by their respective questions. And then how is this 10H the same as 10 in binary? Okay, 10H is hexadecimal, right? And then when you translate 10H in hexadecimal to decimal, that's still 10, right? Because we have 10 in wait, okay, I think I made a mistake there. I'm so sorry, I made a mistake around that side. 10H it would rather be A, that would be the same as 10 in decimal. So then I made a mistake at that side. So it's 10H, right? So let me go back to the first. Okay. Then let me see the other questions before I move on. 10H. Yeah. Okay. Please give me a second. Yeah, gosh, you're right. 10H in binary is actually 10000. Like, yeah, and that would mean that it would overflow. Let me see something. I'm coming. Give me a second, because that would mean that it would overflow. So then it would be more than what we need. As in, we can't specify something like that. So we are trying to see whether it's an invalid instruction or not. Okay, so we have some difficulties because of the 10H. So then because of overflow issues, the 10H part, it won't fit into the instruction like as expected, or as maybe one would normally think. I don't know how every individual thinks, but definitely didn't fit the way I thought it would. So then we'll take the question again. Load JX10H, right? So it's a load instruction. So specify the opcode. We know that the opcode for load is 0000. So 0000. It's 5 bits, right? And then the addressing mode is from immediate to register because it's 10H to JX, right? So 10H being the source and JX being the register. So that's 0 here, right? 0. Okay. So when you convert to 3 bits, that's 000. So 000, right? Okay. Then we move to the next part of the instruction. The next part of the instruction is the first operand. Now the first operand is a register, right? And is the destination, and it's JX. When we count from A, B, C, D to J, with A being 1, B being 2, A being 0, B being 1, C being 2, D being 3, and so on, we get J to be 9, right? So then JX, so 1 0 1 0 1 0. That's for 9, right? Is that for 9? 1 0 0 1. Sorry. 1 0 0 1. Then the next operand is 10H, which is an immediate, and it's 10H in hexadecimal. 10H in hexadecimal is this. So a simple way to convert from hexadecimal to binary would be using the binary coded format. So 0 is 0 0 0 0, with each hexadecimal digit representing 4 bits, and then 1 is 0 0 0 1. So in the end we get 1 0 0 0. Now when we append this to the instruction as our next 4 bits, we append it like this: 1 0 0 0, and then an extra 0. Now this exceeds 4 bits, right? It's 5 bits. So the last bit will be chopped off, right? The last bit here. So that's what I'm getting. Initially I thought we chop off the 1, but it seems as though we chop off the last bit rather. So we append the 1 0 0 0 1 0 0 0 0 to the instruction, and then we chop off the last bit. Since if we add the last bit to it, it exceeds the instruction size, right? So we end up having this. So yeah, this is it. Let me see. So this is for load JX 10H, right? Okay. Then the next question is, sorry for any inconvenience, course. Next question is load BX JX, but then the JX is in square braces. So let me see, are there any comments? Okay. So JX is in square braces. So we take the instruction like this: load BX 16. Sorry, that's 16. Load BX JX. Now it says in the question that memory references are made using a register in square braces, which means that this register in square braces is actually making a memory reference. So what that means is that we go into this register JX, then whatever you find in that JX place is a memory location, and we take whatever is in that memory location and put it in BX. So then, but aside from that, we reference it the same way, like we translate it the same way as a register location. So then the first 3 bits represents the addressing mode. Now since JX is a register location, but it is making a memory reference. Then this instruction has an addressing mode of memory to register, because what GX in brackets actually means is that go to GX and find a memory location, and then whatever is there, put it in BX. So it's a memory to register addressing mode. And in memory to register addressing mode, for our YKS architecture, memory to register is number 4, which is 0100. But then we write 100 because we need to chop out the first bit for it to become 3 bits. So 100. Okay. Then our next 5 bits is the opcode. The opcode for load is 00000. So then we have 00000, right? Then our next operand, which is our destination, is BX. BX in the table is the second register, which is represented by 1 in decimal. Now 1 in decimal translated to binary is 1 still, so it will be 0001 because we need 4 bits. So 0001. Then the GX, well, GX, as we said, is 9, right? Because when we count down from A to E and then we correspond with these numbers, we'll get GX being 9. So like we said in the beginning, and 9 is 1001, so 1001, right? So the second instruction's machine code is this, right? Okay, and then the first instruction's machine code is this. So we move on to the next one, plus GX BX. Now what's the addressing mode of this? The addressing mode is register to register. So BX is the source and GX is the destination. So from BX to GX, which is register to register. So the addressing mode is 1, right, in decimal. 1 in decimal is the same as 1 in binary, but we pad it with 3 extra bits. Sorry, we pad it with 2 extra bits to make it 3 bits. So let me write the actual assembly instruction here. So the actual assembly instruction is plus GXBX. So plus GXBX. So we have 001 for the addressing mode. Then the next thing is the opcode. The opcode for plus is 00010. 00010. Then the next thing is our destination, which is GX. Now GX, as we said, is 9, right? It's represented by the decimal 9, and 9 in binary is 1001. Then our next operand, which is our source, is BX, and on the table BX is where is it? BX is 1, right? So 1 in binary is 1, but we pad it with 3 extra bits to make sure it's 4 bits. So we get 0001, right? So the machine code for plus GXBX for this particular architecture is this, right? Okay, then move on to the next one. Next one is move it, then AXJX. The addressing mode here is register to memory location, because you realize that this register is in square braces, which means that it is we're actually making a memory reference. We are referring to a memory location. What this means, as we said here, is that going to register AX, right? You see a memory location, right? And then you use that memory location as the value there. You understand? So in essence, register AX is specifying a memory location. You understand? So the addressing mode is register to memory location. So there are 2 register to memory locations here. But then the first register to memory is memory location specified by another register, and the second one is memory location specified by intermediate value. Sorry, immediate value. Now we can see that the memory location is specified by a register, which is why it's in square braces. So we take the first one, which is 3 in decimal, right? So then, sorry, which is 2 in decimal. So the addressing mode is register to memory, where the memory location is specified by another register. For example, bracket AX. You understand? Okay. So since that then the addressing mode is specified by 2 in decimal, then it's the same as 0010 or 010 because you need only 3 bits. So 010, right? Okay. Yeah. The instruction is move it AXGX. So move it AXGX. Move it AX in square braces, then GX. So you have the addressing mode. Then we need the opcode for move it. The opcode for move it is, where is it? Okay. The opcode for move it is 00001, right? Okay. So we specify it here 00001, right? And then the opcode for AX, which is our next operand, is 0000 because AX on the table is 0, right? And 0 in binary is 0, but we need 4 bits, so we pad it with 3 extra bits. Then the next one is GX. GX is 9, right? It's represented by 9 in decimal. So when we change it to binary, we get 1001. So 1001. So move it AX in square braces JX has its machine code to be this. Then the next one is load BX 08H, right? So the addressing mode is immediate to register because 08 yeah is a hexadecimal value. So then it's an immediate, right? And it's specifying a memory location, right? So immediate to register, right? Okay. Wait, okay, I'm coming. Let me see something. Give me 1 second. Sorry, the 08 is not representing a memory location. It would only be representing a memory location if it was in square braces, as referenced here. So if you have something like 08 in brackets, that's when it represents a memory location. So I think 08 raw like that is just an immediate. So immediate to register. Immediate to register is the first one. So 000. Um, Papa. Yeah. So then we are on load bx08 each. So load bx08 each. So let me see struggle. Load bx, sorry, 08h. The addressing mode is immediate to register. So that is 000. Then the opcode for load is forget it. The opcode for load is okay 5 zeros. So 00000. So 00000. Then the opcode for bx, sorry, the code for bx 0. Okay, yeah. So 0001, because bx is in is represented by 1 in decimal, right? Okay. Then okay. So yeah. And then 08h. So we translate it to binary. 8 in binary is 1, right? So 1000, and then this one is just a bunch of zeros. So then we get yeah. So the H is for this one. Yeah. So then we have 1000, right? Okay. So that will be the end of it. So load bx08h has its machine code to be this, right? Okay.
What questions are they asking now?
The last one is load AXBX, where AX and BX are both register locations, but they are in square braces. So which means that they are memory references. So we go into that register location, get a memory location, and then we use that as our value or as the memory location for that particular operand. So the addressing mode is memory to memory, but memory to memory is not possible here, right? Is it possible? Yeah. So they are like memory to memory operations are not supported. However, they may be implemented in the higher level assembly language. In this case, the assembler will simply convert the instruction to two separate instructions and use any available register as an intermediary storage. So then for this, we are supposed to be the assembler and we are to convert the memory to memory instruction as into two separate instructions. So let me write it down first. Load AXBX. So load AX. Load AXBX. I hope that is right. Yeah, load AXBX. So then what do we do for this one? We can make it something like load. So here's the destination and here's the source, right? So we are loading something from BX into AX, right? Sorry, I'm not loading something from AX into BX, some from BX into AX. We are loading something from a memory location stored in BX to a memory location stored in AX, right? but then we can't do memory to memory. So we need to split it into memory to register and register to memory. So, well, you can split it any way you want, but I'm choosing to split it memory to register and register to memory. So you pick any register that is available. I'm going to pick something like PX because I don't know, it's far and we haven't used it in any of the instructions. So then we'll have something like load. So I'll split it into load BX PX, right? And then load AX PX. So then, because we are assuming that register PX is available, right? Is it actually PX? P seems too far. Okay, that's okay. So then we are assuming that register PX is available because in the question or in the preamble they gave us, they were like direct memory to memory operations are not supported. However, they may be implemented in the higher level assembly language. In this case, the assembler will simply convert the instruction into two separate instructions and use any available register as an intermediary storage. So we are assuming that the register, sorry for reading the question again, but we are assuming that the register PX is a readily available register and we are using it as our intermediary storage, right? So then we've converted, we are assembler now and we are converting the instruction into two separate instructions and we are using register PX as our readily available register, right? So then instead of loading from BX straight into AX, we load from BX into register PX, which is available now. Then later we load the value that we put from sorry, so I made a mistake here. We're not loading from BX to AX, but we are loading from a memory location that is in BX to a memory location that is in AX, right? So then we'll load from the memory location that is in BX to the register location PX. Then when we are done, we'll load from the register location PX to the memory location that is in AX. I hope that is clear. So this instruction will now be simplified to the handwriting will now be simplified to these two, right? So this is the same as this, or it's roughly the same. It will perform the same instruction given that PX is ready for use. So we now have to compile these two instructions or assemble these two instructions into their corresponding machine code. So for load PXBX, right, the addressing mode is from a memory location stored in register BX to register PX. So it's from memory to register because this is not, we are not taking from the register BX, we are taking a memory location from register BX and we are taking what's in that memory location and then storing it in PX. So it's memory to register. Memory to register is this number 4, where the memory location is specified by another register, right? Which is exactly what we have. So our addressing mode is number 4, and number 4 is how do I pan the screen? 100. So number 4 is 100, right? Okay, so that's our addressing mode for the first instruction. So right now we are treating the first instruction. So we are treating this one, right? So 100. Then the opcode for load is 00000. The opcode for PX. Now PX in the table is 15. So then the binary would be 1111. Then the opcode for BX is 1, right? So then in decimal it will be 0001. Okay. So you successfully assembled the first one. We move to the second one. So load AX in square braces PX. The addressing mode is from register to memory location, where the memory location is specified by AX. Register to memory, where the memory location is specified by another register, is here, number 2. So our addressing mode is 0010. Then for load, our output is 000. Then for AX is the first register, so 4 zeros. Then PX is the 16th register, represented by the number 15. So that's 1111. So then if you're compiling this instruction, we'll compile it. We'll first assemble it into 2 separate instructions and then translate them. So now we have this and then this, right? So this corresponds to this, and then this corresponds to this. So like so. So load AX in square braces BX is this. Right. So when asked this question, I would compile it down to this or assemble it down to this. Okay. Then you can move on to the next question. And then there's F and G. Convert the following machine code instructions to assembly language. So to convert, let me see. The question? Comment. Okay, the comments. Okay, how many comments? Okay, I don't think there are any new comments. So let's move on. So the next question F, is convert the following machine code instructions into assembly language. So I and I. Okay, so I is 000. How many zeros? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So oh yeah, each instruction is 2 bytes, so 16 zeros. 1 2 3 4 5 6. Okay, isn't okay 5 5 4 5. I don't know why I made it now. So 5, then 4 5. So converting it to assembly language, we would have, first of all, our addressing mode is immediate to register. Then the output is this, which is for load. So immediate to register, I to R. And then the output is for load. Then the next, the operands. This is our destination, this is our source. So it's immediate to register. So since it's immediate to register, the source will be an immediate. So that will be 00H. And then the register will be, the destination will be a register. So that will be okay. How do you know? Okay, so we know the last one is an immediate because the addressing mode here was immediate to register. So immediate to register. So immediate is the source. And then the register is the destination. So immediate to register, right?
And we can assume any register.
Yeah, okay, we can't assume any register. We have to assume the register specified by the code.
Okay.
So the register specified by the code 0000 is AX. So we have load AX, then 00H, like that. Okay. Then the next one is 001, then 3 zeros, then 3 ones. Is it 001? 011, 3 zeros, 3 ones. 011, 3 zeros, 3 ones, and then 01, 001. 01001. Yeah, I think 01. Yeah. So that's our second instruction. So this for the first instruction. Right. That's I. Then we're at II now. So since you're at II, the addressing mode is 011, and 011 is number 3. Register to memory. Okay. Register to memory where
Memory location is specified by immediate value.
okay. So register to memory where memory location is an immediate value. So when you go to the table, you see yeah. So number 3, register to memory where memory location is specified by an immediate value. Okay. Then the next 4 bits, next 5 bits are opcode 0000, which is load. Then the next 4 bits, and then the next 4 bits. So you interpret the next 8 bits based on the addressing mode. The addressing mode is register to memory, and register here. So register to memory, which means register is the source and memory is the destination. So here is the source and here is the destination, right? So because here is the source and here is the destination, then that means give me a second. Okay. So this is the source and then this is the destination, which means this is a register and then this is a memory location, and the memory location is going to be specified by an immediate, right? Okay. So here the register specified by 0101 is going to be the set register. That's number 5, because 0101 is 5 in decimal. So counting from here, 4 is EX, so 5 will be FX. Okay. So then this is FX, right? Yeah. So FX, right? So register to memory, but the memory location is specified by an immediate value. Since it's specified by an immediate value and it's a memory location, we put the immediate value in square braces. You understand? And the immediate value is 2, right? So 2 in hexadecimal is 0 to H, right? Okay. So this is 0 to H. So that's the instruction. So II is load 0 to H FX, right? Is it? Okay. Okay, it seems as though I made a mistake when I was writing the instruction, like as in the machine code instruction. So it's 0 1 1 0 0 0. Let me see. So 0 1 1 0 0 0. Then before three extra ones. So 0 1 1 0 0 0 before 1 1 1, and then 0 1 0 0 1 0, and then 0 1 0 1. So 0 1 0 1, like so. So so scratch this. So this is not I, but you can take it as another question. I don't know. So a bonus question. I don't know. So then this I hope it's in the correct form. 0 1 1 0 0 0 1 1 1. Okay. 0 0 0 1 1 1. 0 1 0. Then 0 1 0 1. Okay. Yeah. So then this is the addressing mode, right? This is the opcode. Next 5 bits. Then the next 4 bits is our destination operand. And the next 4 bits is our source operand. Right. Okay. So the addressing mode is number 3. So we have that right. Register to memory, where the memory is specified by an immediate value. But then the opcode is 0 0 0 1 1, which is minus on the table. So 0 0 0 1 1. So it's minus rather. So minus, and then our first, our source operand, which is here, right, is a memory location, but then it's specified by an immediate value. So since it's a memory location specified by an immediate value, we put it in square braces. So then the immediate value actually is 5. So in hexadecimal it would be 05H, right? And then the destination is a register, as we have here, and this is our destination. So the register that corresponds to this, which is 10 in decimal, is which one? A B C D E F G H I J K. So when you count from A to K, you realize that KX corresponds to number 10 in decimal, right? So since KX corresponds to number 10 in decimal, you put KX here because this is 10 in binary, right? So yeah, register. Yeah, register. Yeah, and this place is the destination, and then this place is the source rather. That's right. So it's the memory forget. So the memory, yeah, the memory will get the square bracket, right? Alright, so this one is the memory. So sorry, I made a mistake. So it was registered to memory. So the register rather should be here, and then the memory location should be here. So it's the values will change. So this will be different. So here I would rather specify a register, which is register 5, and register 5 is what is register 5? Register 5 is fx. So fx, and then the memory location will be specified by an immediate, and the immediate is 10. So the immediate will be put in square braces, and 10 in hexadecimal is a, right? Yeah. So 0AH, right? So then the instruction is minus okay, so that is for II. Then III, that's this. So I 1010 1010, then 0011 0011, then 000 0001, and then 0000. So we have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So this is the whole span of the instruction. So we do what we've been doing. Take the first 3 bits as the addressing mode, next 5 bits as the opcode, next 4 bits, and then the next 4 bits. So this next 4 bits will be our source operand, and then destination operand, and then this next 4 bits will be our source operand. So the addressing mode 101 is 5 in decimal, which is immediate to memory, right? So immediate to memory. Then the next 5 bits, which is our opcode, is for minus. So 00011 is minus. Then because our addressing mode is memory sorry, immediate to memory, immediate to memory. Then we are taking from an immediate to a memory location. So here will be an immediate, right? Our source will be an immediate, and it's 00h. So we don't put it in square braces or anything, right? Because it's not a memory location. It's just a normal immediate. So we write it as 00h or just 0h or 0. Or I think you need to, yeah, 0. And then the next one is a memory location. So since a memory location, we can use an immediate to represent the memory location. And then this number in hexadecimal is just 1. So 01h as a memory location. So for I, the instruction is minus 08, sorry, 01h. Zero one h. Then and then 00h. So minus from immediate to memory location, where the memory location is specified by another immediate. The next question, a given single cycle a given single cycle non-pipeline microprocessor implements the YKS architecture. It uses one clock cycle for the fetch stage, one clock cycle for the decode stage, and one clock cycle for the execute stage, no matter the instruction. If the processor takes 26.25 nanoseconds to execute the program in question 2E, what is the frequency of its clock? So where's question 2E? Okay, so there are how many instructions in question 2E? 1, 2, 3, 4, 5, 6. To execute the program in question 2E, and the program consists of 5 instructions. Now, what is the frequency of its clock? For each instruction, remember to take into consideration the time for the fetch, decode, and execute stages. For simplicity, assume the write back stage is embedded in the execute stage, which means we'll have fetch, decode, execute, but then no write back. We'll assume that the write back is inside the execute. So only 3 stages, right? Okay. So I think Papa should take this one because I have to think before I do this.
Hello. Yes, it's Papa, and I'm back. Okay, so let's begin quickly. Let's hurry up and let's end. Right.
I said our background conversations are entering.
Shh. Okay, so this is what is happening in this moment. They told you that giving a single non-pipelined microprocessor implementing the YKS architecture uses one clock cycle for the fetch stage, one clock cycle for the decode stage, one clock cycle for the execute stage, no matter the instruction. If the processor takes 26.25 nanoseconds to execute the program in 2E, right? 2E. That means this program, right? This program, if it takes 26.25 nanoseconds to execute the program, what is the frequency of its clock for each instruction? Remember to take into account fetch, decode, execute stages. So this is what is happening in this case, right? Okay, so what you are going to assume is that every instruction has three main processes, and that's actually true in fact, right? That's actually true in fact. The fetch, decode, execute, and store is the machine cycle for all instructions. Meaning that regardless the instruction, they'll go through the same processes. I hope you understand that. So that's why it's called the machine cycle. Like all instruction, regardless of anything, does it, right? And the system is telling you that it takes one clock cycle to undergo fetch. It takes one clock cycle to undergo fetch, one more clock cycle to undergo decode, one clock cycle to undergo execute, and then they told you that the store is part. The store is called the write back. In this case, it is part of your execute. So this is what is happening, right? For example, if you have to add 4 and 5 to fetch the instruction, it is one clock cycle. To decode the instruction, that is actually 4 plus 5, it is one clock cycle, and to execute the instruction, it's another clock cycle. So it takes 3 clock cycles. If we are loading data from, let's say, from register to memory, right? Let's say we're loading instruction from memory to register, right? We'll fetch the instruction, we'll decode the instruction, and then execute it. Regardless of it, it will take 3 clock cycles. I hope that makes sense. Let me check if anybody has commented. Okay, that means it's making sense. Lovely. So it is telling you that execute these instructions, and I just said that regardless of instruction, it will take 3 clock cycles. So I'm going to go Dora's way and ask you how many clock cycles it will take to implement everything. 1, 2, 3, 4, 5, 6. It takes 6 different instructions, right? So if 3 clock cycles per instruction, it will take 18 clock cycles to clear all these instructions. I hope this math makes sense to you, because each instruction takes 3 clock cycles, and then you're implementing 6 instructions, meaning that it will take 8 clock cycles to finish up these instructions. You understand? And actually, what is the frequency of the clock? So that means that 18 clock cycles, and it's telling you that what is the frequency. So if you watch the last stream, you remember I said that the frequency is equal to 1 over period, and period is in seconds. Period is in seconds. So what will happen in this particular case is that you want to find out how much time that these 18 clock cycles actually take. You understand? And then you use this in your frequency equation, and this will give you your frequency. Beautiful. Right. So it tells you that it takes 26.25 nanoseconds to execute the program, meaning that for these 18 clock cycles, and it takes 26.25 nanoseconds. You understand? 18 clock cycles. So if you want one single clock cycle, because frequency is measured in clock cycles, like if you remember your, I don't know which one safe, like if you remember your physics, right? Remember your physics, period is measured as a cycle. I don't know, this is not a cycle, but like period is measured from cycles. You understand? So you have to look at one cycle, and then the time it will take for it to complete this particular cycle is the period, and then you use this period to calculate your frequency. You understand? Excellent. So 18 clock cycles is equal to 26.25 nanoseconds. One cycle is equal to x. you do your cross multiplication to get 26.25 nanoseconds divided by 18. Sorry for the handwriting here. The calculator. Yes, so you get 1.458 nanoseconds. So this is the time. It doesn't make sense. Okay. I didn't look at the actual instructions, so please let me look at it.
The last one.
The last one we split into two.
Okay. So the last one was split into two, so it changes it. So if this is split into two, that means you're talking about 7 effective instructions. If you're talking about 7 effective instructions, it changes this to become 7. 7 times 3 gives you 21. So this gives you 21 clock cycles. And given 21 clock cycles, this changes this value. So thank you for I think whoever pointed that out. I wasn't looking at it, so thank you so much. This becomes 21 clock cycles, giving you 26.25 nanoseconds. Do the division, you would get. Do the division. You get 1.25 nanoseconds. That seems like a cleaner answer. So that gives you 1.25. Yes. So thank you so much. So that gives you 1.25 nanoseconds for one particular cycle. Right. And it's asking you to determine the frequency of your clock. Right. So if every cycle, one cycle is taking 1.25 nanoseconds, right, then it means that our frequency will be equal to 1 over 1.25 nanoseconds, and that gives us 0.8 gigahertz clock. That's not really fast in our current context, but that gives you the frequency of the clock. And please continue to type in the comments. I see it and I thank you. So K-Duke, I don't know who that is, but thank you again. Excellent. Now question 6. I feel like the stream has gone on for too long, so we are planning on confirming the most probable, right? And then we'll do another stream tomorrow, looking at the time, and then we'll go over everything again. So please, I'm so sorry that it took so long, it's so late. We'll go over it again. So please be sure to revise these and then make it for tomorrow. And tomorrow too, we'll be having a slight revision of assembly for about 15 to 20 minutes. So if you don't know what assembly language is, please join early so that we can quickly run through and then be able to do it. Now let's look at question H. Okay, yes, I'm back. How long would it take the processor in question 2G to execute the same program if it is modified to use a simple 3-stage pipeline using the same clock? Okay, So now let me explain what pipelining is before we begin, because it would make the explanation of the question a little wonky. Right. Okay. So assume that you have a pipe. This is usually a pipe. We assume it's a pipe, right? So we assume this is an instruction queue. Then we have instructions inside. So for example, you want to calculate the mean of the ages of the people in your class. The first thing you have to do is that you have to store their ages in some registers. So we have some instructions doing that. You have to add them to, then you have to divide them by the number of people in your class. So let's say we have these instructions, right? All the instructions are in this queue. They're entering here and they're being executed and then they're being thrown out here, right? So let's say this is store Paul's name, store Azwe's name here, store somebody's name, then you add them, and then you divide them, something like this, right? What can happen is that you store all these instructions in memory. And when you store all these instructions in memory, if you remember from any micro class, you do realize that memory is sort of a bottleneck in your system, because your execute and decode cycles, because they're using gates, they don't actually go according to your clock cycle. They go a little faster than your clock. So what will happen in actual fact is that your processor will just be waiting for your memory to bring in the data, because what happens is your memory has to your address would go to your memory, go and look for the actual data that you want, and then carry it and bring it to the line, and that takes a lot of time, like in microprocessor terms. And the decode and execute is almost instantaneous. You understand? So that's what happens. So what you can do to make this faster is that you can prefetch your instructions. Right? You can prefetch your instructions. So it's like this. Let's use this analogy. Right? You're cooking, and then I'm in the living room, and then you are in the kitchen. And then every single time you need your next instruction, you have to shout for me. Then when I hear it, I have to process it, search on the internet, and then get your next, what you have to do next. So you put the rice on fire, and then you shout, what am I supposed to do next? Then I will look for the next thing in your recipe, and I'll shout that, oh, please go and heat the stew. You understand? It takes a lot of time to do that. So what you can do is that you can when you're putting your rice on fire, you can shout out that, oh, what is the next instruction? Then you write it down. So right now you're in the kitchen, but you have the instructions written down. So for example, this is rice, this is heat your stew, this is, I don't know, mix them, something of the sort. You understand? So you have something like this. You've called me out, and then you have the instructions like you've already written it down. So you don't need me to, like, at the particular moment that you are looking to execute it, you don't really need me. That's what happens here, right? Let's say that, let me check the comments again. Okay, I think everything is fine. So this is what is happening, right? Let's say that there are 3 people in your class, right? You need to take Kofi's age. Take Amma, still typical Kofi and Amma. Then you take Kwame's age. Then you add Kofi to Amma. Then you add Kofi and Amma, the result of that, to Kwame. And then you divide by 3. And these are all stored in memory. So the time that you would take to get the instruction, take Kofi's age, it will take time. Then take Ame's age, it will take time. What you can do is that you can get some bank of registers waiting, so that while your decode cycle is going on, you can fetch your next instruction, which is take Ame's age. Then while your execute is going on, we are saying take Kwame's age. Then while your next one is going on, you can take Kofi plus Amma. What happens is that your processor works a lot faster, because right now you don't have to be going to memory for every single instruction. You can just take it from your register bank, which is in your microprocessor. This is what is called pipelining. Pipelining is when you use inbuilt registers to hold some data that otherwise you'd have needed to go for in memory. You understand? So now there's the question. Actually, they're saying that using a three-stage pipeline, right? How long would it take the processor to execute it? Right now you have 7 instructions. Right? What will happen is that you have a fetch here, you have a decode, you have an execute. In your first clock cycle, what will happen is that your first instruction is fetched, right? And nothing happens at decode and execute. In your second instruction cycle, your decode is your instruction one goes. So this is instruction one. This is instruction one. In your decode, in your third clock cycle, so this is first clock cycle, second clock cycle. In your third clock cycle, your instruction one is being executed. You understand? But then what happens here? What happens here? Nothing goes on here. You understand? So we could implement a pipeline process, right? That actually make use of this, and this. Okay, let's go. And this is the point of the pipelining. You understand? That means that whilst in your second clock cycle, whilst your first instruction is being decoded, you can fetch your second instruction. And whilst your actual instruction is being executed, you can decode your second instruction, and then you can fetch your third instruction. Right? Now, after your first instruction has been decoded, what will happen in your fourth clock cycle is that your second instruction will be decoded, will be executed, your third instruction will be decoded, and your fourth will be fetched. Right. In your fifth cycle, the same thing will happen. Fifth instruction, fourth instruction, and third instruction. In your sixth clock cycle, you have your sixth instruction being fetched, your fifth instruction being decoded, and your fourth instruction being executed. In the seventh clock cycle, you have your seventh being fetched, you have your sixth being decoded, and you have your fifth being executed. But because there are only 8 instructions, when after your seventh instruction, your system can't fetch anything again, right? So that means your seventh instruction is decoded, but nothing occurs here, and then your sixth instruction is executed. In your ninth cycle, nothing happens and nothing happens here. Your seventh instruction is executed. So you see, apart if we were to do it normally, what happens is that it will take 3 clock cycles for each instruction. So 3 clock cycles times 7 instructions, giving you 21 clock cycles. That's what we did first. But in this new pipeline system, you can see that we have 9 clock cycles. I mean, so 21 clock cycles has been reduced to 9 clock cycles. You can see the obvious advantage. You understand? So that's why we pipeline, right? And they told you that how long would it take the processor? So right now, if 1 clock cycle was 1.25 nanoseconds, then 9 clock cycles will be 9 times 1.25 nanoseconds. That would be 11.25 nanoseconds. You shorten the time from 26.25 nanoseconds to 11 more than half. You more than half the time. You understand? So from this particular instance, you've solved the question. It will take 11.25 nanoseconds to execute the same program if it is modified using a 3-stage pipeline. The 3-stage pipeline, I feel like I didn't explain. The 3-stage pipeline talks about the fact that it has a fetch, decode, and execute. Right. That's what the pipeline means. Right. It can fetch multiple, it can decode in multiple. So if you look at the microprocessor project that we did, if you really looked at yours, I don't know about you, but for our group, we couldn't fetch in the same cycle because we're using one data bus, right, for the entire thing. Right? So if you fetch her, you have to wait till another instruction cycle before you can actually fetch again. You understand? So with the 3-stage pipeline, what's happening is that you have a separate data bus for your fetching, you have a separate data bus for your decoding, you have a separate data bus for executing. That's what makes this possible, right? Because if you had one data bus that everything was running on, you couldn't fetch. Your instructions will clash with what you actually want to do. Hope you understand. So that's how to solve the question. I feel like we've taken a lot of time. So please, we'll get to the rest of the statements later. But the beauty about the questions is that most of the questions are justify questions. If it's based on understanding. So for this one, I'm not solving it, but for this particular one, okay, this one is not a justify question. It's actually a true. It's actually a statement that you have to state. You understand? For this one, it's a justify question. It depends on you. It depends on how you think about it, how you produce an answer. This one too, it depends on you. This one, in fact, it tells you that which one would you choose and why. You understand? It's a choice that you make. The questions are very, very interesting. And for this one too, this one has a clear-cut answer, but the way you explain it, that would define whether it's true or not. You understand? So please, let's make some time tomorrow for it. Let's make some time to move for it. I hope you really understood. If you didn't understand, please go back and then try to get it. But Elisa's email account is always open. Please send in your questions. Our DMs are always open. Please send your questions so that if we can't explain it in the chat, we'll explain it tomorrow during the stream. You understand? I think it will be 6 a.m. or 6:30 a.m. in the morning. So please let's set our alarms and then get it well. We thank you so much for joining us, and we'll see you. Have a lovely night. Bye bye.
See you,